Ladies and gentlemen, my name is Maciej Filiński, and with Paweł Wachel and Kuntils we prepare article Low-dimensional decomposition for nonlinear finite impulse response modeling. And I would like to present you our result. So, first, we consider single input, single output, time invariant nonlinear finite impulse response system with memory length d, described by equation 1 and 2, and the output of the considering system is nonlinear characteristic g with arguments v, where v is the vector of the inputs from time n to n minus d, and additive output disturbance e. And our goal is to find hidden internal structure of the system, of course, if exists. And the second goal is to decomposition of the system into smaller, short-term memory elements. In the first figure, we can see the system under consideration, block-oriented representation of the system. And in the second figure, we see the internal structure of the function g, of the block g. Here we can split the function g into smaller short-term memory elements, here with two inputs each. Let's talk about the assumption of this problem. First, the system has a finite memory of known length d, and the unknown but bounded nonlinear characteristic g. The second assumption is the input is an IID sequence, and the third one is the noise is zero mean IID sequence with a finite variance, and it's independent of inputs. Let's talk about the notation. First, Xi1 is the subset of indices set, and Xi2 is the complement of set Xi1, and we say that G is separable with respect to Xi1 and Xi2 if we can split function g into sum of two functions g xi1 and g xi2, where g xi1 and g xi2 is a function depending only on the variables with indices from xi1 and xi2 respectively. So we note that g is separable with respect to xi1 to xi-me if and only if separability factor s is equal to 0 or close to 0. Here we have the estimators. In the equation 3 we have the separability factor s, and we can split it into two parts. First, s1 depends only on the passive experiment, and s2 depend on the passive and active experiment, but the active experiment depend on the input sequences of the passive experiment. Let's talk about the algorithm. First, data generation for active experiment. This algorithm has two inputs. First is the input sequence from passive experiment, and the second input is the candidate separation scheme, which we are check. And the output of this algorithm is the active experiment input sequence u. And in the 6 and 7 line, we have the pretty complicated lines pretty complicated operation, but behind this two-line is the a pretty simple method, and I can explain how this two-line work in the simple example. So let's take Xi1 equal 1 and Xi2 equal 2 and 3. So the system memory length D is equal to 2. And the first step of this algorithm 1 is the split the input sequence for 2 halves, and we create new input sequence for Xi1 and Xi2. And for Xi1 we take first and second inputs from the second half, and the third input from the first half. And for Xi2 we take first and second inputs from first half, and the third one from the second half. And the last step is to merge these two sequences into one input sequence for active experiment. Okay, here we have the the second algorithm. So here we searching separation scheme, and this algorithm has one input, the input-output measurement from the system, and the output of this algorithm is the separability factor for Xi1 to Xi d+1. And this algorithm has 3 steps. First, we design input sequence for active experiment using algorithm 1 for Xi_p equal 1 to 2p. The second step is to excite the system with input sequence and measure the output sequence. And the third step is to compute separability factor for this Xi_p. And the output of this algorithm, of course, we have the separability factor for each Xi. And we know that if the function g is separable with respect to Xi1 and Xi2, and p is less than q, then function g is also separable with respect to Xi3. And we use this property of this algorithm to minimize the number of active experiments. So let's have a look at the numerical experiment. We have 3 systems. System A, here we have the system which are non-separable, so we can't split the function g into smaller elements, and below is its corresponding equation. The second system, system B, is partially separable, so we can split here the function g into smaller short-term memory elements, here with 2 inputs each. And here is the corresponding equation of this second system. And the third system, here we have the fully separable system, so we can split function g into d+1 small short-term memory elements. And below is the corresponding equation. Now let's talk about the result. First, we run our simulation for different number of samples for different value of noise variance, and for memory length of each system equal 9. And we note that the separability factor for Xi10, for last Xi, is always separable. So the value of this factor for Xi10 is the reference value for decide which separable scheme are separable and which not. So in the first and second system, the reference separability factor for Xi10 is almost equal to 0, and we have easy way to decide which are separable and which not, because the value of non-separable separability factor S is much higher than the reference value. Here we have the same situation, but in the third system we have some problem, because the value of reference separability factor for Xi10 is much higher than in the system A and B. But it's not a big problem, but the value are much higher. And here we have the figure represent the table data from table, and here we easily can see that the value of separability factor for separable scheme are much lower than the rest of the value, but in the system C we can see that the bar of are much higher than in the previous two system. And the conclusion, first, the method potentially simplifies system identification by reduction of problem dimensionality. So we can split one big problem into some number of the smaller problem. And then second, the method supports inference about the rule and property of the particular short-term memory substructure. And this method has some drawback. First, we need to do active experiment for each separation scheme. And the second drawback is that we can use only n over d plus 1 output samples. So we lost some of this value. Thank you for your attention, and goodbye.